Vector is very important in biomechanics because we deal with many quantities that have both magnitude and direction. For example, when we analyze a force, we represent force using vectors. So in this class, I showed this example. You know the tension, which is 250. So let's say the tension is 250 Newton here. Then obviously, say the hip is aligned with the origin of these coordinates, and then I want to break down this force into x, y, z positions. So I want to get the component of x directional force of the rubber and y directional and z directional, and also what's the angle, the orientation of this vector in terms of theta x, theta y, theta z. So in order to analyze it, just represent this force as a vector and analyze the vector. So like shown here, basically we represent the force acting on the rubber as a vector. So it has a direction, it has a magnitude. Let's say from here to here, that distance represents 250 Newton. Then how to represent the force? If you look at the vector, you have to identify three important elements of the vector. The first one is the point of application. In this physical example, actually the rubber is attached on the foot. So that's the point of application, that's the point of action. And this length of the vector represents magnitude, and this is a line of action, this whole line. And then right now I just use a vector as a u, but you can just name your vector like a or r, and then in my notes I use superscript like arrow, so this quantity represents the vector. And then please notice that since we have a point of applications, which I call the B, and then it's just pointing to the A is the point on the ground. So actually this vector, the tail is a B and the head is A. So the vector toward is heading toward A from B. So that's why I use this notation, the vector pointing A from B, or sometimes we use this notation as well. So from B to A. Because we care about the point of applications, so from where is kind of important. But actually when we define the vector, actually there are two different types of vector. One is a free vector, and the other one is a bound vector. So in the free vector is generally, when it comes to vector, we usually talks about the free vector. So free vector is just care about the magnitude and direction. So that means the point of applications is not important. But in the bound vector, in addition to magnitude and direction, we also care about the point of application. So actually this vector that I showed on this slide actually belongs to the bound vector. So right now, let's say if we just talk about the free vector, right now there are two vectors between the left and right side. But in terms of free vector, these two vectors are equivalent. It is exactly the same. But if you talk about the bound vector, because on the right side the vector starting from this origin, however on the left side vector starting from any arbitrary point on the xy plane, so we consider these two vectors are different. But in terms of free vectors, and these two vectors are exactly the same. In general, the vector just refers to free vectors. In our example, we represent these vectors from pointing A from B like that. Then how to represent vectors? When you represent vector, we used component vectors. Okay, that means every vector can be broken into x, y, z components. So let's say we have a vector in the space for like that. Then let's say pointing A. So we just call this a vector. So this one actually pointing toward has this a from O. Then this a vector can be broken into x, y, z components. So which means this one has a x component, y component, and the z component like that. And then I, j, k is our unit vectors. So the unit vector is aligned with a x-axis, but its magnitude is just 1. And likewise, we have a j vector, and also we have k vector along the z-axis. If you think about the 2D like that, xy, and then if you have a arbitrary vector a, then you can break down this one is ax and this is ay. So your vector a is axi plus ayj. So these are called a component vector. Okay. So how to represent vectors? So we break the vector into x, y, z, and then that's the way we generally represent our vector. Let me just draw the one kind of x, y, z coordinate. So let's say this is my x and this is my y and this is a z, and then each axis has a unit vector I, and this is j, and this is k. This is k. And then in our example, our first vector starting from here pointing to the ground A. So this is, we call the B, right? So this is a point A on the xy plane, and this is a force vector right now. And then as we imagine this vector, we can also imagine a unit vector of my force vector. Let's say this is E. So unit vector has a magnitude of 1, okay? And then however our force vector is 250 Newton indicated in our example. Okay, then I call my force vector just R, okay? And then this my vector pointing to A from B. Or as I said, I can write down like that. Okay? And then if you look at this my vector, you imagine that if I break this vector along my z-axis and any other vector on x, y plane, maybe I can think about, let's say I have, let's say this vector, and then I have another vector like that, okay? And then I call this one is the vector and point toward A from O because this is our origin. And then this vector I can call this is B from O, okay? Then if you look at this triangle here, then we can easily think about our this RBO vector plus my force vector here. So let me change our color. So this is my force vector. is equal to what? This one, okay? As you imagine that RBO, RAO can be represented by component vector. That means this one has a RAO vector X component I and plus RAO vector Y component J and RAO and Z component K. Okay? And then this RBO vector can be represented by component vector as well. So this is X component of I, and this is RBO Y component J, and this is RBO Z component K, right? So that's why your RBA, which is our force vector, is equal to, if you just shift on the left side for RBO to the right side, then you can just subtract each element from element for RAO vector. So what I mean by is that RAO X component minus RBO X component and everything for I, and then RAO Y component minus RBO Y component J and plus RAO Z component minus RBO Z component K, like that. So this is the way we represent our force vector. But right now, if I a little bit simplify this one, we know that for RBO vector, so this is aligned with the K. That means it doesn't have any XY component. So basically, this one doesn't have any XY component. It has only the Z component. So basically, this one should be just 0. Okay. And then, if you want to get the magnitude of RBA vector, I want to get the magnitude, then you know that this is square of each element for x, I, j, k and square root. So that means RAO x component square plus RAO y component square, and then RAO z component minus RBO square. So that should be the magnitude. Then right now, I want to get the, let's say, if I want to get the unit vector, my unit vector of R oh, I'm sorry, I have to correct myself. So this one should be A, here is A and B here, okay? So I'm sorry, so this one should be A and this is B, because this force vector is heading to A from B, okay? So I just switched it mistakenly. So this is unit vector RAB. So I want to get this unit vector of my RAB. So how you get the unit vector? So unit vector has a unit, the magnitude is 1. So unit vector E can be calculated like RA over B and divide by each magnitude, right? So in a case, we still contain, this still contain the direction. The direction is still same as RAB, but because we normalize it, which is magnitude, the magnitude should be 1. So that's why this one should be our unit vector. So however, the RAB itself has its 3 components for I, J, K components. So you can just write down this one is x component, and then the magnitude I plus y component divided by the magnitude of your whole vector j, and plus RAB is z k over magnitude. So once you define your magnitude, okay, then you just divide the magnitude from each component for x, y, z, then that can be a component of your unit vector. So let me a little bit talk more about direction of a arbitrarily vector in this space. If I just make another like a coordinate system like that, so let's say this is x and y, and let's say this is z, and then you define any arbitrarily a vector. So let's say this is a u, but if I make this one is more realistic, so actually this u is pointing not on the plane on xy, actually this is on the x space. So if I just make the guideline, now did you figure out the u is pointing to xyz space, not on the plane? Okay, and then this one can make another line here and another line on this. Then this arbitrarily u vector can be represented by component vector. So u x component I, okay, which means if you project the u onto the x-axis, so from here to here, so this one should be ux, right? Because if you project this u vector along onto x-axis, that's ux. If you project this u vector along the y, then this should be your uy, okay? And then if you project this one onto the z-axis, so this one here should be uz component. So that's why u can be represented by like that. Okay. Then we can make the angle. So let's say if you define the angle between this vector, you can angle between the vector and x-axis is theta x, like that. And then the angle between the y and the vector, let's say this is theta y, and the angle between the u and then z is theta z, okay? Then just thinking about the uy, what is a uy? So actually, as you know that, let's say this is a u, and then let's say this is x, and then if you project u along this onto x-axis, then this is theta x, then this from here to here, so this is ux, so u magnitude cosine theta x should be uy, right? Because if you project a u onto the x, and then between angle between u and x axis is theta x. So u magnitude cosine theta x should be ux. So we want to change this one, replace ux with that one. Okay, so cosine theta x I, and then uy is u cosine theta y j plus u cosine theta z k. Then if you rearrange this one, this is a u and cosine theta xi, cosine theta yj, and cosine theta zk, like that. Then when I talk about the unit vector, so when I talk about unit vector for this u, so let's say I want to define my unit vector. So let's say this is u and then this is e, because the e is unit vector of my arbitrarily vectored u. So my e is equal to u divided by u magnitude, right? This is the definition of unit vector. So if you look at these equations, then if you divide these equations using the magnitude u on both sides, then on the left side is this one, on the right side is just cosine theta x I, and on the right side is this one and cosine theta zk. So we know that this one becomes our unit vector, right? Unit vector. So basically we know that this should be the component of my unit vector I component, x component. This is unit vector y component, and this is unit vector z components. And then we call this x, theta y, and theta z is direction cosine. So this theta x, theta y, theta z actually determine the orientation of arbitrary vector in the space. So that's why this is called the direction cosine. And then the unit vector of any arbitrary point can be represented by the cosine direction theta. Okay. Okay, so right now, if you look at on the left side, okay. So on the left side, the u vector is generally this form. So which means ux ui plus uy over uj, and uj component, this is y component, divided by uk, because on the left side I substitute u vector with this form and then divide by the u magnitude u. That's why left side will become in this way, and the right side is still using this one. Okay, cosine theta x and cosine theta y I j and cosine theta zk. So which means cosine theta x is become this one. So if I just write down here, so cosine theta x is equal to ux, the vector component x divided by the whole magnitude of u. Okay, cosine theta y become uy divided by u magnitude, and cosine theta z becomes uz for u divided by u. So from here you can get the theta x, theta y, theta z. So cosine theta x is u, x component of u, and cosine theta y become u, y component of u, and cosine theta z become u, z component u, magnitude. Theta x is cosine inverse ux u, and theta y is cosine inverse u, y component u, and theta z becomes cosine inverse u, z component, magnitude of u. Okay, so that's the way we can get the direct cosine. If you want to determine the orientation of unit vector of any arbitrary vector, then you can determine the orientation of vector using theta x, theta y, and theta z. Let's try to solve this one. So let me just show this picture. And first, okay, I want to define, let's say this is RA from O, and then from here to here RBO. Okay, so we know that R like that, and then our RAB is RA minus RBO. Okay, then what is RAO? What is RAO? So we know the length. So from here to here is 40 centimeter. Okay, and then from here to here is 30 centimeter. So RAO becomes 40I and plus 30J. Okay. And what is RBO? RBO has only one direction, so height is 8 centimeter. So this is 8K. So basically your force vector RAB becomes 40I and 30. This is not just distance vector. Okay, so 40I and 30J and minus 80K. And then what's the length? What's the length of this vector? So I want to get this magnitude. Okay, so if you get the magnitude, that's 40 square, 30 square, and 80 square. So this one becomes 94.3 centimeter. So that's the length of this vector. Okay, then what is the unit vector? I want to get the unit vector. So unit vector is from here to here, let's say, and let's say this is magnitude E. What is the unit vector E? So we learned that unit vector can be represented by this one. Right now the U is refers to RAB. So RAB vector and divide by the magnitude of RAB, right? So our RAB is 40I and 30J minus 80K divided by the magnitude is 94.3. So that's the unit vector. That's the unit vector. So this is 40 divided by 90.3I and 30 divided by 90.3J and 80 divided by 94.3K. That should be your unit vector components. And then we know that this one is cosine theta x, this one is cosine theta y, this one is cosine theta z. Which means if you think about, if you align your vector, let's say you align the b along this x-axis, for example. So you just imagine that you align your coordinate system like that. So this is x and this is y. Then x is from here to here, so this one should be theta x. And then angle between your y and this vector, which means from here to here, is theta z. And then theta z is this vector between the z direction and this vector. So this one should be theta z. Okay. So that's why if you want to get the theta, your theta x should be cosine inverse 40 divided by 94.3. Okay. So this is 64.9 degree. Theta y is cosine inverse 30 divided by 94.3, which becomes 71.4. Theta z is cosine inverse 148 degree. So right now we know that my force vector actually this vector represent force, okay? Force A from B. Then we know that this is the magnitude of whole thing and then unit vector, okay? And then the whole magnitude is already known as 250 Newton. And what is a unit vector? Unit vector E is cosine theta xi and cosine theta yj and cosine theta zk, right? So we already know the cosine theta, cosine y, cosine z. That is this value. Okay, this one cosine theta, cosine z, cosine theta z. So if you want to get the component of x, y, z component of f, then you can just directly write down this number, okay? I, j, and k. So that's why if you just multiply this one, 106I and 79.7 k j and minus 212 k. So this is x component of your rubber tension, this is y component of your tension, and this is a z component of your tension. So basically upward of a z component is positive and downward is negative. So this rubber tension is going down to the ground. That's why this one becomes a negative here.